Good morning, everyone. So I was in Spanish class this morning during what is it? Second period. I was in Spanish class con la maestra Viera, and there's this girl in the class who's like the brainiac of the class, who's answering all the questions and stuff. And I got put into a breakout room with her, and I said, "Oh, tú eres muy inteligente." And she didn't understand what I said. So I was like, okay, uh, maybe ella no es muy inteligente. um, ¿Cómo se dice maybe en español? ¿Quién puede digitar en el chat? ¿Cómo se dice maybe en español? Tal vez. Tal vez ella no es muy inteligente. Gracias. Tú me ayudas. Ok. Nosotros empezamos. Oh, I should say it like Maestra Veras. Entonces, nosotros empezamos. Okay. So we are done. Well, we're not done with the concept of energy. We're going to keep coming back to energy because it's like a key concept in physics. But we're going to move on from that for the moment, and we're going to start learning about something called momentum. Okay? Momentum. And so momentum is denoted by P. This is a little bit confusing because we just learned about power. Power is typically an uppercase P, and momentum is typically a lowercase p. And so momentum, the formula for momentum is mass times velocity. Okay? So this is the formula that we're dealing with today. All right? If you want to remember it, a really easy way to remember it is to write it as mv equals p, so that it's MVP. Okay, do you guys know what MVP means? Type it in the chat if you know what MVP means. We can get the units of momentum by noticing that momentum is mass times velocity. Okay, so mass is kilograms, velocity is meters per second. So momentum has kind of weird units. They're called kilogram meters per second. Oh, someone typed in most valuable player. No, MVP does not stand for most valuable player. It stands for most valuable physicist. And that's you guys. You guys are the most valuable physicists to me today. Okay. People walk into that one every year. I always ask my class that. Okay. If you have more than one thing, so there's multiple parts to the system, then the total momentum of the system is just going to be the sum of the individual momenta. Okay? So the total momentum. One thing I want to point out is I want to just kind of really briefly compare and contrast momentum with kinetic energy, because kinetic energy has a similar formula, right? Kinetic energy depends on the mass and the speed, just like momentum does. Okay? But if we think about kinetic energy, see how kinetic energy has v squared, okay? So kinetic energy is, no matter your direction, you have the same kinetic energy. If you go 5 meters per second to the right, you have the same kinetic energy as if you go 5 meters per second to the left, because you square it, the velocity. So if the velocity is negative, you square it, it becomes positive, okay? Momentum, on the other hand, does not have velocity squared, okay? So if you go a different direction, your momentum is not the same, okay? So we would say, so kinetic energy does not depend on direction. So we would say kinetic energy is a scalar, okay? Scalar is something that does not depend on direction. So for example, temperature is a scalar. You know, you don't say that something has a temperature of 5 degrees northward, okay? You just say it has a temperature of 5 degrees. Momentum, on the other hand, has a direction, and so it is what's called a vector, okay? So they're not the same thing. They depend on the same variables, but they're not the same thing, all right? Box that in. Okay, so momentum is particularly useful in a certain type of problem, okay? So whenever two or more objects collide, you should think of momentum. Okay, so this is the type of scenario where momentum is the most useful, when two things are colliding, okay? Why is that? Well, it's because there is something called the law of conservation of momentum. So type it into the chat if you know what a conservation law is. What does a conservation law mean in physics? I will wait. Como se dice to wait in Spanish? Is it atender? I'm going to guess atender. Tal vez la palabra es atender. In French, it's attendre, is wait. Je vous attends. Okay, no one wants to answer what a conservation law is. Okay, that's fine. You do you. Oh, okay, someone answered. Conservation laws means nothing is lost. Yeah. So what the law of conservation of momentum says is that the total initial momentum before the collision is equal to the total final momentum after the collision. Okay? So that's called the law of conservation of momentum. So, anyways, for the rest of the class, we are going to do a couple of examples involving the law of conservation of momentum. Okay? And so all of these problems that I'm going to do are going to take place in outer space. Okay? And there's a reason for that. It's because let's suppose, for example, that you collide with something on Earth. What often happens is that you give, so you might collide with something, so you might gain momentum or lose momentum or something like that. But because you're in contact with the Earth, it's not really you, just yourself, that gains the momentum. It's you and the Earth. Okay? And because the Earth is so massive, it basically absorbs all the momentum with no noticeable difference. Okay? So all these problems are going to take place in outer space to sort of remove any other things that could also have momentum in the problem. Okay? So this first example, I like to call it a recoil velocity problem. Okay? And so what we have is an astronaut. Okay? And the astronaut is floating in outer space. And the astronaut has a rifle. Okay? And initially, the astronaut and the rifle are at rest. And they have a mass altogether of 70 kilograms. Okay? Then, the astronaut fires the rifle. Okay, so here's the bullet. The bullet has a mass of 0.15 kilograms, and it is headed this way at 200 meters per second. Okay. And so the astronaut is going to recoil. Okay. And we want to know what is the recoil velocity of the astronaut. So, I said you should think about it as a collision problem. Think of momentum when you have a collision problem. This is a collision problem just in reverse, right? If you thought about the reverse of this scenario, it's the bullet and the human coming together. So this is kind of like a reverse collision. Okay. So again, if you fired a rifle on Earth, you fire that rifle, and the recoil is absorbed not just by your body, but by your body plus the Earth. Okay. If you're in outer space, there's nothing else to absorb the recoil besides you. So you're going to go flying backwards when you fire the rifle if you were to do so in outer space. Okay. Um, so I'm going to write an expression for the initial momentum. Well, initial momentum, if we look at momentum, it depends on the velocity. And because everything is at rest initially, all those velocities are zero. So the initial momentum is 0 kilogram meters per second. Okay? The final momentum is made up of two parts. Okay? The first part is the momentum of the bullet. So the momentum of the bullet is m times v, so 0.15 times plus 200 meters per second. So again, that direction is important when we're talking about momentum. The momentum of the astronaut, well, the astronaut has a mass of 70 kilograms, okay, and has a final velocity that is unknown. So we just leave it as a variable. So see how we have mv plus mv, okay? So this is the total final momentum. This is the total initial momentum. Now, the law of conservation of momentum says that the initial momentum is equal to the final momentum. So I can say 0 equals 0.15 times 200 is 30, I believe. Let me just double check. Well, 10% would be, 30 plus 70 V final. Okay. Subtract the 30 over, negative 30 equals 70 V final. Divide by 70, we get that the final velocity is, okay, minus 0.43 meters per second. All right. So a couple things about this. The first thing is that notice how the recoil velocity is negative. Okay. The recoil velocity is negative. So if you fire the bullet in the positive direction, you're going to recoil in the negative direction. All right. That's basically a reflection of Newton's third law, because for every action, there's an equal and opposite reaction. So if you put a force on the bullet forward, the bullet puts a force on the rifle backwards. Okay? So you start to move backwards. So in the homework, if something recoils in the negative direction, I will expect you to put that minus sign in there. Okay? The second thing I want to talk about is, notice how the velocity of the bullet is 200 meters per second, but the velocity of the astronaut plus the rifle is only 0.43 meters per second. So the astronaut is going much slower than the bullet. Why is that? It's because the astronaut is more massive. So if you have two things that hit each other, or you have a recoil velocity kind of situation, the more massive one is going to have less recoil. Okay? So that's completely what we would expect to happen. Okay? So those are just a couple of comments. This is also why if you're on Earth, you don't go flying backwards when you fire a rifle. It's because it's not just you absorbing the recoil, it's you and the Earth as a single object absorbing the recoil. And because the Earth is so massive, you don't have a backwards velocity that is noticeable. Okay. All right. So for our next example, we are going to have what is called a completely inelastic collision. So what is a completely inelastic collision? A completely inelastic collision is a collision where things collide, and after they collide, they stick together. So what does it mean for two things to be stuck together? To be stuck together means that they have the same velocity. Okay? If they had different velocities, then they would be drifting apart, right? If one is going faster than the other, then they would slowly drift apart. But because they stick together, they have the same velocity. So for this example, we will have two astronauts that are drifting towards each other. Okay. This astronaut on the left has a mass of, let's say, 70 kilograms and is drifting to the right at, let's say, 11 meters per second. Okay. This astronaut has a mass of 40 kilograms and is drifting to the left at, let's say, 5 meters per second. Okay? And just to spice it up a little bit, we'll say that these astronauts are in love with each other. So they're having an embrace. So because they're having an embrace, they're going to collide. And when they collide, they're going to hold on to each other. And so it's a completely inelastic astronaut collision. Okay? And so the question is, what is the final velocity? And there's not just one final, there's not two final velocities because they are stuck together. So that means they have the same final velocity. Okay, so there's only one variable. Okay, so what is the initial momentum of this system? Well, we're going to have mv plus mv. So for the left astronaut, we have m, which is 70, times v, which is plus 11, positive 11. And then for the other astronaut, we have a mass of 40, and we have a velocity of negative 5. Keep in mind that it's going to the left, so it has negative momentum. So that's going to be 770 minus 200. So our initial momentum is 570 kilogram meters per second. Okay. The final momentum is going to, again, be the momentum of the first person plus the momentum of the second one. So 70 times v final plus 40 times v final. Notice how I'm using the same variable for both of their velocities because they are stuck together after the collision. They collided and held on to each other. Okay? So that allows us to collect like terms. So we get 110 v final. In future problems where we do completely inelastic collisions, I will just immediately go to this step. So from the standpoint of momentum, when two things are together, we just add their masses and think of them as a single object. Okay? So in the future, I'll just go directly to that step for the final momentum. Now, final momentum is equal to initial momentum, so 570 equals 110 v final. Okay? And so dividing by 110, we get 5 point plus, the final velocity is plus 5.2 meters per second. So after the collision, they end up drifting to the right, okay, while holding on to each other. So that is called a completely inelastic collision. That's a type of collision that we will come back to quite often. Let's do another example. Let's suppose, so this example is about collision graphs. So what do graphs of collisions look like? Okay. So what if we have a velocity time graph of a collision? So we have time in seconds, we have velocity in meters per second. So let's just say that this is a velocity time graph for a 3 kilogram object. Okay. So maybe this 3 kilogram object is cruising to the left at 10 meters per second. So because of Newton's first law, if you're just coasting through outer space, your velocity is going to be constant. So your velocity is just going to be a flat line like that. Okay? But when you have a collision, that velocity is going to all of a sudden change. It's going to very rapidly change when you have the collision. Okay? So, so I don't know, maybe the velocity goes really quickly changes to plus 4 meters per second. Okay? And then after the collision, it stays constant again, according to Newton's first law. So this is what a velocity time graph of a collision looks like. You have a constant velocity, and then you have the collision, and all of a sudden the velocity changes really rapidly, and then it's constant again, because now you're just drifting. You're done with the collision. So whatever amount of time that took, that would be the time span of that collision. So the time at which the collision occurs would be whatever the time coordinate of that is. So maybe that's at 5 seconds. Okay? So now what if we had a 2 kilogram object and it has its own velocity time graph? Okay, so maybe its velocity time graph looks something like this. It's going okay. So maybe it's going with a velocity of plus 6 meters per second. Okay, a constant velocity of plus 6. And then at 5 seconds, the collision occurs. Okay, so its velocity is going to abruptly change to another value. And so the question is, what is the final velocity of this 2 kilogram object? Okay, what is the final velocity of the 2 kilogram object? So we can use conservation of momentum. What is the momentum before the collision? The total momentum before the collision. Well, I have a 3 kilogram object, and remember the collision occurs at 5 seconds. So basically anything to the left of 5 seconds is before, and anything to the right is after. Okay? So before the collision, the 3 kilogram object has a velocity that's sitting at negative 10 meters per second. Okay? Now we have the initial momentum of the 2 kilogram object. So we have 2 times its initial velocity. So before the collision, its velocity was plus 6. So we have 2 times plus 6. So the initial momentum is negative 30 plus 12, which is negative 18 kilogram meters per second, is the initial momentum of the system. After the collision, so after the collision is what is happening beyond 5 seconds, okay? So we know that this 3 kilogram mass, after the collision, its velocity is now plus 4 meters per second. All right. And then the 2 kilogram object has a momentum that's 2 times whatever its final velocity is. Okay. So this one is going to have, this one is not a number, it's an expression because we don't know what the final velocity is. So we have 12 plus 2 v final. Initial momentum is equal to the final momentum. So we have negative 18 equals 12 plus 2 v final. Okay. Subtracting the 12 over says negative 30 equals 2 v final. Dividing by 2 gives negative 15 meters per second is v final. Okay. So what that means is that this velocity is going to drop down to minus 15, which maybe is down there somewhere. So the velocity is going to go really abruptly and then sit at negative 15. Okay? So this is how you analyze collision graphs. They look, they look flat, and then once the collision occurs, they abruptly change, and then they're flat again. Okay? All right, so I think that's my lesson for today. I think I taught you everything you need for the quiz, so I will see you in the Zoom room.